Hello and welcome to this webinar. My name is Knud Valdemar, and today I will go through import, processing, and inversion of full decay DC/IP data. And I will follow the workflow manual that we link to in the description to this webinar quite closely. So if I move too fast somewhere, or if you need further clarification of some of the things I show, you can look in the manual. And I would also like to point out that we have to get through quite a lot of stuff today. So I will demonstrate how it works, but I won't go too deep into theory about anything, and I won't go into file formats and stuff like that, because we simply don't have time to do that. So again, I will refer to the workflow manual, where you will find the descriptions of the different file formats, and you will also find the references to resources where you can read more about the different topics that we discussed today. And as always, you are welcome to ask questions in the Q&A session. Then I'll try to answer them as we go along. And maybe I will answer a few of them after we are done. And otherwise, we'll also send out an email with answers to all questions and links to further reading. Let's get started. So this is how Aarhus Workbench looks when you first open it, except that you can see I have some recently opened workspaces. You won't have those if you don't have worked with Workbench before. But the first thing to do in the beginning of every Workbench project is to create a workspace. And you do this by selecting New. Then you select which folder to place the workspace in, and you give it a name. I'll call this Webinar 1. And you always also put in your username. This is used to track who's making changes in the workspace. You can see that in the workspace log. And then you can select whether you want to go directly into the data import mode after opening the workspace. I'll not do that because I'll show you where the menu is, so you can also find it later. But if you just want to import data right after creating your workspace, you can put a check mark in this checkbox. Then you have to provide a name for your map. I'll just let it be with the default now. And then finally, you have to select a coordinate system. And this is because Aarhus Workbench is centered around this GIS map, where the position of every data set is plotted, and where you can also see all your inversion results and boreholes and everything you import. So it is important that you select the coordinate system that you would like to work in. And the most important thing here is that it is a coordinate system actually covering the area that you are working in. And today we will be looking at some data from Denmark. So I will select UTM zone 32 north. And you can see we really have a lot of different coordinate systems in here. So unless you would like to use some very obscure, very specialized coordinate system, it should hopefully be in this list. And after doing that, you can just press finish. I just point out one thing, that when you import data in your workspace, if they're in another coordinate system, you'll have the option to convert them into the coordinate system you select here. So the coordinates of your data sets doesn't necessarily have to be in the same coordinate system as the one you select here. I'll just select finish, and then the workspace is created. So this is a completely empty workspace, which is not very interesting. So we'll start by importing some full decay DC/IP data into this workspace. And you do this by selecting Database Explorer and then Import. And because we don't have any databases to hold our data in this workspace yet, we will have to create a new one. So I'll select new database, and I'll just call it DCIP. Once you have created a database, then you will be able to find it under existing databases if you import more than one line into your workspace. And as you can see, we have a number of different import options. We have the most used one, which is the DAT format, which is shared with REST2DINF. So this is the uppermost one here, REST2DINF standard and extended formats. And then you can see that we have some custom imports for different instruments, for iris instrument data, GTD data, and finally we have the option, if you have bought the streamed ERT package, then you can import streamed data. And then we also have some direct imports for ABEM terameter data. And you can see these imports, they are all related to ERT IP data. If you have bought other modules as well, then you will also see the imports for these, for example, for airborne data and ground-based EM data. But I'll just select OK here. Then you will see this screen where you can select the data set to import. You can see I've done a bit of a preparation, so I'm already in the right location, but otherwise you'll navigate to the folder where your data is located, and then you'll select your data file. Then when you work with data in Aarhus Workbench, you always have to have a noise model, and if it's not measured and estimated in the instrument, then you can start out by applying a uniform noise model. In this case, I'll use a 2% estimated error for the row A data and 10% for the IP data. This is usually a good starting point. Then you can select whether you want to import topography data directly from the data file, if it's included in that one, which is in this case. You can also add it from an external elevation model, a DEM, digital elevation model, or you can import it from an EVP file, which is another option. This is just a text file where you can put in the global coordinate information and the topography instead of typing it directly into the data file. And you can read more about these different file formats in the workflow manual. Then we also want to apply global coordinates, UTM coordinates, and in this case these are also included in the DAT file. As I said, they could also be in the EVP file. And if they are in the EVP file, then you have to point to the EVP file in this field. And then again, you have to select which coordinate system that the coordinate data are given in. So if you have measured them with GPS, then you will usually set up the GPS to use a specific coordinate system, and then you have to select the same coordinate system here. And in this case, they are in the same coordinate system as the workspace, which is WGS 84 UTM zone 32 north, which is there. Okay. And then finally, there's this field, filter waveform file, where you have to import a file which contains information about how the data was measured, and we'll look at that file in a moment. So it's the exact same as selecting the data file. You can just select the EVP file here. And once you have done that, you press import. Then it reads the data file and imports the data. And then it says import done. Do you want to add the data to the workspace? Usually you will select yes here. And then if you have several different maps, you usually don't have that in a workspace, but it is an option. Then you can select which map to add the data to. And finally, you have to provide a name for the processing node. We'll talk about more later what a processing node is. And then you can select whether to view the dataset right away or not. I'll not do that now because I'll show you how you open it if it's not directly after an import. As I said in the intro, I won't go too deep into the theory in this webinar, but I promise to show you the ini file that was provided together with the dat file at the data import. So I'll just show that to you here. And it looks like this, and it basically contains the information about the transmitted current waveform. So how long was the current turned on and turned off, and when were you actually measuring? And you can read much more about this in the workflow manual that we link to in the description of this webinar. And we will also send out an email afterwards with answers for any questions and links to this manual and other resources. So now the data file have been imported, and it can then be found in the Workspace Explorer. So you can see that this tree over here is starting to be built, and over here, once you have built a nice large workspace for a project, everything will be found over here. So you can see we are now under the map, my map, and then different data types would be shown here. So this is electrical resistivity tomography, and then we have imported the line demo line, and you remember that I earlier called this a processing node. This is because this holds the measured data, which can then be processed or edited. And then once we start doing inversions of the data, they will then be found under this node. You'll see that later. But as you may have noticed, when I checked this checkbox, some dots appeared on this blank area, and that is because this is the GIS map that I talked so much about. But right now we haven't actually added a map, so it looks a bit boring. So I'll just show you now how to add a map. So you have different options for adding a background map, and they're hidden down here. So I'll just move myself. So over here, this tree that will be built up over here is all the map layers. So right now, the only thing visible on the map is the electrodes from this data line that we have imported. But once you start to add more elements, they will show up over here. And now we can just try to add a background map. And you have two options for doing this. You can add an offline map by selecting this folder. So this is a map you have on your computer already. It can, for example, be in the form of a geotagged TIFF file, or you can select this one to use a web-based layer. And I'll just do it that today. So, for example, I can select the Google Maps aerial photos, and I'll just select OK, and then just take a few moments to load. And now you can see where your data is actually located out in the real world. It's the black dots here. We can actually change the color of them now, so they are a bit easier to see. You just do that by selecting the layer here, and then you can say edit display. Then you can, for example, make the dots a bit larger, and we can change them to another color, red, for example. So now you can see they are easier to see. So now we have imported our data. We have added a background map, and you can see the data here. And we can now go two ways. We can either run an inversion right away, or we can take a look at our data and maybe do some editing before doing the first inversion run. I'll do that. So to look at the data we have imported, we select the processing node up here. We are on the Workspace Explorer tab now. And then we navigate to the Data Processing tab here in the top menu. And then we select Process Data. And then the processing window will open in a moment. This is quite a big data set, so I'll just take a few seconds to load. And now you can see the processing window, which contains quite a lot of different windows that I will talk you through now. But the first thing I'll show you is, and usually I'll do this on 2 screens, and I'll have the processing window on 1 screen, and then the Workbench window on another screen. But you can't really do that in a screencast. So I'll just show you like this, that when you move the cursor around down here in the Pseudo section, you can see we have this blue point on the map moving, so you can see where every single data point is along the line. And a lot of things in Workbench work this way, that you can either select them or just mouse over them, and then you can see the location of them in the real world, which is a pretty neat feature. And also see up here, we have the location of all the electrodes in the survey, and you can see it's plotted with the profile distance on the x-axis and the elevation on the y-axis. And if I select one of the electrodes here, you will also see, then I'll get this large red dot where that electrode is located. And now I have, of course, selected to have all of the electrodes red. If I hadn't done this, then this would be clearer. But you can see there's a large red dot here. And you can see if I select another electrode here, then another point will light up. But now I'll just maximize the processing window again and talk you through it. As I said, up here we have the electrode positions plot, and you can see the y-axis here looks a bit weird. That's because I haven't set the precision high enough to show. So I'll just, if you click the axis, then you can edit how it's displayed. And I'll just do this here. So okay, values format, that's how the labels on the y-axis are plotted. I'll just select to include a decimal place here. Then you can see that it's the elevations in meters on the y-axis, and we have all the electrodes here. And a really neat thing about this is that if you select one electrode, then down here in the data profile and in the Pseudo section, every measurement made with that electrode will be highlighted. It can be a bit hard to see here, but you can see you have some gray points here. They are the measurements that include this electrode, and as well down here in the Pseudo sections, you can see these gray points dotted out across the Pseudo section. And out here in the IP decay curve window, you can see all IP decays measured with this electrode. And it's the same all the way around. If I select a data point down here in the Pseudo section, then you can see the 4 electrodes included in this, or the 4 electrodes used for this measurement. And again, you can do the same up here in the data profile. But now I'll just talk you through these windows one by one. So electrode position, then we have some focus steps out here, and you can see now there's a check mark right next to every single one of them. I'll just remove all of those, uncheck all, and then I'll just select a few, maybe 2. And you can see when I select Pseudo focus steps out here, something happens in here, and this is the data profile plot. So when I select a focus depth here, then all the data points with that focus depth is plotted in here with the profile distance on the x-axis, and the apparent resistivity on the y-axis. And right now this is a logarithmic axis. You can also select to have a linear axis if you want. You can do it like this, and you can also set the minimum and maximum limits manually if you want that. Then you just have to remove the check in automatic, but I'll just keep the automatic setting on here. This is quite a nice plot to edit data in, because you will expect the variation along such a line like this to be fairly smooth. You won't expect to have some extreme outliers, and you can see it's varying fairly smooth. Here in the middle we have something that could maybe be some noise, but it could also be real data. I'll just see if I can find a better example. Up here, yeah, something like this will be quite unusual to see. So this is probably some kind of error. So you usually remove data like this by selecting the data and pressing the Alt key together with Q. So now I have removed that data and will not be used in the inversion. And this data profile right now, we are showing the measured apparent resistivities. They can also be used to show the full decay IP data. So you change that up here, and now it says row A data here. But then you can select to show the different IP windows. So you will show one IP window that is the same time in the IP decay for all data points. And I'll just turn on the automatic access here again. So you can already see here that the IP data, they are much more noisy than resistivity data, and a lot of outliers have been removed here automatically by the import when we imported the data, and that's probably because that it's negative values. And you can see it's not only the data profile that changes together with the data profile, the Pseudo section will also show the IP values instead, and you can also see that a lot more of the data have been removed automatically already. Then we have the Pseudo section down here. Most of you probably already know what a Pseudo section is, but it's simply every single data point plotted at the position of their focus point. So it is the focus depth. So out here we have an elevation axis, and then it's the distance along the profile, and then the color of each point is the measured apparent resistivity, and you can see the color scale down here. In this case, it goes from 2 to 200, and you can edit the color scale by selecting settings, and then you can edit the color scale here. And we have a separate webinar about how all this color scale editing and creation works, so I won't go further into that right now. And what this plot is good for is also to find outliers, to find data points that are bad, and this can be because of couplings or background noise or poor electrode contact for single or several electrodes. But what you want to look for here is like up here, it's outliers. So if you you sort of expect to see this plot varying smoothly, and it does vary quite smoothly in this case. But if you, for example, if I had a bright green dot right here, then that would probably not be a good data point. So I'll probably remove that. And like in the data profile plot, you can select data points in the Pseudo section, and you can select Alt Q, and then they will be removed. So when a data point is removed, it means that it will not be used in the inversion. You can see they are still there, they are still stored in the database, and you can activate them again. But if you have removed them by pressing the Alt key and Q, then they will not be used in the inversion. And another way to remove data point is by selecting them and then right-clicking, and then you can say toggle in use instead of using the keyboard shortcut. You might also have noticed that when I select points down here, then you can see that something happens up here, that you get some blue lines up here. And these lines, they are the full decay IP data. So they are measured after you turn off the current, then you get this IP decay. And now I'm showing the IP decays for these selected points down here. And you can see you have the chargeability on the y-axis, and then you have the time down here. And right now, both axes are logarithmic. And you can see that in this case, you have really nice, smooth IP decays. If this is not the case, and you see some weird spikes from background noise, then again, like in this window, you can again select points to turn them off. So you select them and you can press Alt Q, and then you can simply remove part of the decay so they are not used in the inversion. You can also select this checkbox. Then instead of removing the points individually, then if you just select some point at a decay and press Alt Q, then you will remove the entire decay. And you can also select to hide the points once they are removed, so you only see what you are actually keeping. So the last part of this processing window that we haven't talked about yet is this sounding plot down here, which is empty right now. So to get something displayed in that window or in that corner, you'll have to select sounding up here in the upper left of the screen. And then very analog to the focus depth that you use to select which data points were plotted on the data profile, then you can select a focus point along the profile. So instead of working in the depth area here, now we are working on the in profile distances. So as I, for example, select 170 meters, 171 is the closest, then you will see a sounding curve down here, which corresponds to you can call it a 1D sounding. So now I have selected all the data points that are have the focus along this 170 meter point along the profile. So it will be all these data points. They will then be plotted with the focus depth on the x-axis and the apparent resistivity on the y-axis. Then we have two more tabs up here. We have the statistics tab, which basically contains some information about the survey, the first and last electrode positions, the different focus steps, the number of data points, number of electrodes, and all that kind of stuff. And then we have the processing tab. And you have a few options in these tabs. So the first one is IP filter. So these settings only apply to the full decay IP data. The DC values aren't touched at all. So the first one here is minimum number of data points. And what this does is that if you, for example, select 5 here, then any decays with less than 5 data points activated will not be included in the inversion. And you can see you can select 2 and 8 as well. Then you can do some filtering on the IP decays. Now, for this data set, the IP decays are very, very nice, but sometimes you see them having a lot of bends or noise, which will make them kind of zigzag here towards the end. And then you can try to automatically filter those out by putting in a slope filter. So if the slope, that is how sharp this line bends, is above a certain threshold, then the rest of the decay will be removed from the inversion. And sometimes you will see bends at the start of the IP decays as well. And if you don't want to remove data from the start of the decay, you can say that the filter shouldn't start or shouldn't look at the decay before 100 milliseconds or 0.1 seconds. So anything that happens in this part of the decay will not be filtered here. And then you also have the option to delete the curve from the first negative data point. So then you'll only have positive IP values. And then if you select apply, then the filter will be applied to your data set. And you can see that these data are really nice, so it didn't really change anything here. Maybe if we look at some of the deeper data, we'll see an effect. Yeah, you can see we have a few, be a bit hard to see, but we have a few gray lines here, which are data points that have been disabled. Then when we looked at the import, I talked a little bit about the noise model. So maybe you have noticed that every IP decay here is plotted with error bars, and the errors plotted here, they are the noise model that we applied in the import. So we put a 10% standard deviation on the IP data, and we put 2% on the DC data. And you have two options for editing this. So for the DC data, you can simply change the value from, let's say now it's 2%. You can maybe change it to 5%. Then you can see the error bars grow. I'll just change it back to 2%. Or you can do it for the individual data points. So you can do that by selecting a data point or a few data points, and then you can use the Alt key together with the number keys. So now I'll, for example, press Alt and 3 together. Then we have increased the standard deviation of these points to 30%. And then if I click this button again, then you can see that this doesn't affect these points. They will still have the manual value that I've put in. I'll just change it back to 10% here. But this is not the case for the IP decays. So if I select a few data points, then I'll have a few IP decays over here. Then you can do the exact same thing. You can select an IP decay, and then you can press Alt 4, for example, in this case. And then you'll see the error bars, they are increased. But for the IP decays, if you select recalculate STDs over here, then you'll see that any manual edits you have done are reversed. So you need to set up your noise model in the processing tab here first, and then you can do manual edits afterwards. If you do it the other way around, your manual edits will be overridden. Then I just need to talk about the two last fields on this form, which is the uniform ipstd standard deviation and the standard deviation threshold voltage. So the uniform ipstd is the standard deviation that is added to all the IP data points. And in this case, it is set to 10%. We can just try to increase it to 20% and see what happens. Then you can see the size of the error bars is doubled. Just turn it back down to 10%. And then we have the STD threshold voltage, which is in millivolts. And what this does is that it will increase the size of the error bar of the standard deviation the closer the data points are to this threshold voltage. So you can use this to apply larger standard deviations to the data laid at the end of the decays. And the reason you want to do this is because the data at the end of the decay is closer to the noise floor, so they have a poorer signal to noise ratio, and therefore you would like to put less emphasis on those in the inversion. I can just try to change it to 0.8, for example, and then you'll notice that the error bars, they grow a bit, especially for the late part of the decay when I select the recalculate STDs. So that was pretty much the last of the settings in the processing window that I wanted to talk about. But maybe I should just round off by with a bit of explanation. So I have talked a lot about error bars and STDs and standard deviations in this last part. And these standard deviations, they are used in the inversion to weigh the data points. So the larger the standard deviation on a data point is, the less this data point will affect the final inversion results. So if you have some data points that are not that you are not quite ready to delete completely, but you are not completely sure that they are good data points either, then you can increase the standard deviation on these points instead of removing them completely. So once you're done with all this this editing, you can press save, and then when it's done saving, you can close the window. So this brings us to the part where we will actually have to run an inversion, but I just want to make a few final remarks on the processing. So I have shown you a lot of different processing and editing options over the last half hour, and it's important to say that you won't have to do this necessarily for every survey. Sometimes you can just import the data and run the inversion right away, and it will fit nicely and you'll have good looking results. In other cases where you have had more challenges in the field, maybe had some equipment problems and where there's more background noise, then you will probably have to do a lot of edits to your data to get good inversion results. So that's always something you have to figure out from time to time. But now I'll show you how to run an inversion of your data. So again, we select the processing node which holds the edited data. Then we go to the inversion tab, and then we select this LCI button to run a 2D inversion for ERT data. And here you see the inversion setup window. You can choose between a 1D and a 2D inversion. We will do a 2D inversion in this case. And then we have some different inversion types. These are different parameterizations of the inversion problem. So if you just want to do a regular resistivity inversion where you don't invert the IP data at all, you'll select this one. And then you have a number of different options for performing an IP inversion. I'll select the maximum phase angle in this case. And I'll just show you an extra feature of Workbench. If I press F1 on my keyboard now, then my computer will open a browser. And then you will be taken to our online help wiki. And the neat thing about this is that no matter where you do this in Workbench, you'll be taken directly to the relevant page in our wiki. So you can see in this case, it's a short explanation of each of the different inversion types you can run. And I'll just show it to you again in the inversion setup on the next page, which we'll come to by clicking next. Because here you can see this is where you control the inversion. And there's lots of settings here. And again, you can press F1, and then you'll be taken to the wiki page, which explains all of these different settings. And I'll just show you a few of them. So we have some different inversion types. Today we'll be running a smooth inversion, which is a many layer inversion with fixed layer thicknesses. If you run blocky or sharp inversions, then it will use some different norms. So this is the normal L2 norm. The blocky is the L1 norm. You can edit the number of layers. You can select where the first and last boundary, so how deep your inversion goes. And it will these numbers will be suggested based on the dataset, but you are free to change them. If you change them, you have to remember to press update afterwards, so it recalculates the layer thicknesses. Then you can select how many CPUs you want to use for the inversion. So this is just a regular laptop, so I don't have that many CPUs. I'll just use 2 in this case, because I'll also still have to record this webinar while inverting, so I'll not use all my resources. And then you can select the maximum number of iterations. Then you can also set up a starting value for each layer, both for the resistivity and for the different IP parameters. And you can edit the constraints. And again, I'll suggest that you read the workflow manual and the wiki page to learn more about all of these settings, because it will be too much to go through all of them right now. And I'll just show you can also switch to table view. So basically, this information in this table is the exact same as you can get plotted over here. But if you prefer to see the exact values, then you can use the table view. And then to actually run the inversion, you'll have to select run down here. And then the inversion progress window will open in a moment. Here it is. And this is quite a big inversion. So it will take maybe an hour or so to run. But as the iterations appear, you will see a plot here with the residual on the y-axis and the number of iterations on the x-axis, and then this window will tell you when the inversion is done, and you can close the window. And like every good television chef, I have of course prepared an inversion in advance that we can look at. So here we have a workspace where the inversion have already been performed. And this was, as I said, quite a big data set. So it was right at the limit of what my old laptop could invert. It took nearly 2 hours. But we have some options if you have data sets that are too big to invert on your local computer. Then we both have a system to send off the inversion to be run at a local server if you have a big server for running inversions and calculations in your office. And we also have a cloud service where you send the inversion off to a server in the cloud and perform the inversion there. So instead of having to buy a huge computer for yourself, then you can simply just rent it for the few hours every month that you need to use it. You can read more about that on our webpage, or you can send us an email if you're interested to learn more about the options. But as you can see now, we have an inversion result under the processing node. So to see the result, I select it and say select show result. So here it is. This is the inversion result window. And again, you have a few different options. So right now we are looking at the resistivity model, and you can see we have quite a lot of interesting features, and that the inversion is quite detailed. And if you want to look at the chargeability model instead, you just select that up here. Again, it will just take a few moments to change. You can see the chargeability model up here. And maybe you have noticed that there is some shading at the lower part of these plots. This is the depth of investigation, which is calculated as part of the inversion process. So this basically tells you that below this this limit, you shouldn't trust the inversion results too much, because they are more driven by the starting model and the constraints than the actual data. And you could also see that for the IP model, the depth of investigation was much shallower than for the resistivity model. And this is again because what I talked about earlier, that the signal to noise ratio for IP data is not as good as it is for the DC measurements. Then down here you can see the DC residual. So this basically, the DC residual pseudo section. So this basically tells you how well the inversion have fitted all of the data points. And you can see the color scale down here. It goes from 0 to 3.5. And how this works is that if you have fitted the data within the error bars, then the residual will be below 1. So it will either be green or yellow. And if you haven't fitted it within the error bars, then it will be above 1. So if it's just outside of the error bars, you'll have these orange colors, and if you haven't fitted the data very well, you will go over to the purple colors. And you can also see the forward model. So that is the forward model that the inversion came up with, and you can then compare it to the original pseudo section down here, and you can see that they are pretty close to each other. You can also add more views if you want to, so then you can compare the forward model and the pseudo section directly, and you can see they are actually quite close to each other. And in the same way as you could in the processing window, you can select the data points here, and then you can also see the IP decay for the individual data points. And now I'll just put the automatic access on. Now the neat feature here is that the error bars you see plotted here, they are the measured data points, whereas the blue lines, the blue line, is the forward model. So here again, you can see how well the data fits. You can see the forward model lies well within the error bars. So that's pretty neat. And you can even do edits to the data again. So if you're not completely satisfied with your inversion, if you have some of these late IP points, for example, that you can see cannot be fitted, then you can simply select them. I'll just select a few points here, and then you can remove them again, like you could in the processing window, by pressing Alt Q. And you can do the same for the pseudo section. You can also edit the data directly in the pseudo section. And a good plot to do this from is the residual plot, because here you can see, okay, this data point that wasn't able to fit very well. So maybe you have to change your inversion settings or something, but you can actually also just delete the data point from the result window right away by pressing Alt Q. this was all I had to show to you today. Of course, some would say that this is actually when the fun starts, because now you have imported some data and run an inversion. Of course, now you would normally maybe add more data lines, which you can do in the same workspace. So then you can have all the data lines from the survey plotted in the GIS window, and you can start to make visualizations and profiles and interpretation with all of the data. But that will be for another webinar. So thank you for listening, and now we might have time to go through a few questions.